Good morning. My name is Howie Granite, and I'm the Director of Business Development with Inventus Power. And here with...
And I'm Alias, Head of Engineering for Inventus Power.
And today we're going to speak about battery backup solutions, some of the options, advancements, and safety involved with those particular packs and designs. So a battery backup unit, or a BBU as we term it, are designed for intermittent power interrupts for systems, and some of them will support minor power interrupts, anywhere from 30 to 90 seconds, and then some of the more sophisticated or larger scale ones will be able to support a graceful shutdown. And each one of them is designed to ensure data integrity, and in the case of a graceful shutdown, an easy launching system once the regular power is restored. In a BBU solution, there are many options that the system architect has to weigh and consider when he makes or she makes that decision as to how the battery backup is going to support the system. Now, in many solutions, including today's on-premises, UPS is pretty much a common way of getting your battery backup, and that's an uninterruptible power supply. However, you may have certain systems out there, and this is heavily used in the data storage application, that you may have a BBU module actually on board that data storage blade as part of that system. There's also a lot of new solutions out there that are modular power supply units that offer battery backup as an option in one of those power supply unit shelves. So there's a couple of different power ranges that you'll traditionally see in each one of these type of applications, where the onboard of the blade server is only supporting that blade, maybe 1U, maybe 2U high. That may be 100 to 200 watts in power. Power shelf system, though, could be anywhere from that 100, 200 watts up to 3 kilowatts per blade or module in that type of option. And a UPS, at least in our regards, single phase 12 or 48 volt, might be anywhere from 1.5 kilowatts to 3 kilowatts. Those are all scalable depending on how much power is required for that system or how much runtime is needed. So if we take a look at a virtualized system, as I'm showing here, essentially you can get battery backup in each one of these particular modules with the exception of the network switch. And that is, again, part of the challenge for the system architect to determine what are the concerns with the amount of runtime required, the latency issues within the system, what type of voltages, and what is the power architecture already in that system. So what you don't want to do is be redundant if you don't need to, but essentially when you have a clean sheet of paper, you have to make that decision, where do you want battery backup to reside? So I'm going to toss it over to Alias to continue the conversation about
Thank you, Howie. So before we talk about design options for a backup battery, let's discuss some of the unique challenges that we encounter with batteries for data storage applications. Typically, BBUs have a very long calendar life requirements. Usually it starts out with 2 years in storage at elevated temperatures, and then 5 years operational. So we need to find cells that can survive that long, still provide enough energy to handle a backup event at the end of its life. BBUs also require very high output power. Some fire hose dumps can require up to 5 kilowatts of power from one BBU. As we search for cells, we will need to find cells that are designed to handle that much power. And two of the worst things that we can do to a lithium-ion battery is to keep it fully charged and keep it at an elevated temperature. And guess what? That is exactly what happens with BBUs. BBUs are kept fully charged, ready to go, so they're ready to handle a backup event at any time, and they're in a very high temperature environment. Again, the cell selection is very critical to find which cells can handle this extreme requirements. Another big issue with BBUs is the ability to have accurate state of charge and state of health data. Most fuel gauges require discharge and charge cycles to keep it accurate. Since BBUs are not being discharged often, the fuel gauge can become stale. So we need to find ways to periodically do partial discharges while still be ready to handle a backup event. This may require BBUs to have extra capacity so we can do these partial discharges and still support a backup event. Thermal mitigation is also a big design challenge, considering that we are in a very hot ambient environment and the pack is outputting a very high discharge output. We need to make sure we're not overstressing the electrical components and cells beyond their temperature limits. Most critical is the cell. Most lithium cells are spec'd to a max of 80 Celsius for skin temperature, including overshoot. And if you start at an ambient of 50 Celsius, you only have a 30 C margin, which is not very big considering the amount of discharge power that's coming from the BBU. So we need to look at component selection, mechanical design, and software design to actually manage the heat. We also need to understand how to design the pack to ensure that we don't have a thermal runaway. We need to make sure if a cell experiences an issue that it doesn't propagate to the rest of the battery. So we need to add mitigation to prevent that. There are also many regulatory items that we need to account for in the design to pass some of the standards. Go to the next slide. So within lithium-ion chemistry, there are many options to choose from. Some of them will work for BBUs and some of them will not. Lithium cobalt is a very high energy density chemistry and was used primarily for laptops and cell phones. The issue with this chemistry is that it has a very low power density and it is not as safe as the other chemistries. This solution is actually not recommended for BBUs. Most preferred option is the NMC or NCA technology for BBUs. They offer a good energy density and power density. These types of cells are commonly used in power tools. Iron phosphate or LFP can also be a good option for BBUs. They offer very high power density, is one of the safest lithium technology, and they can handle high temperature excursions. But their big drawback is low energy density and higher costs. But with the additional safety and thermal mitigations you have to add to the other chemistries to keep them safe, a total LFP BBU solution is coming very close to the cost of an NMC or NCA solution. And with the recent advancements in LFP technology bringing the cost down, LFP can still be a very viable solution for BBUs. One of the critical design elements for BBUs is finding cells that can provide high power. This is an example of a discharge curve for a very high rate and 18650 NCA cell. It can provide up to 30 amps continuously for the duration. And as you can see in the graph, the temperature rises very quickly. So we need to find cells that are very low impedance so they don't generate a lot of self-heating. We also have to ensure we have heat mitigation features in the BBU, such as heat sinking, fans, or active cooling. The key is to ensure that we keep the skin temperature of the cell to be below 80 C at the end of its life after a full discharge. The next couple of slides shows roadmaps of different cells for BBUs. So you want to try to pick cells from the pink region as they offer high power density cells. As you can see, we pretty much hit the wall with high rate 18650s at about 3 amp hours. Typically, energy density is not too much of a concern for BBUs. It is typically the power density that becomes a driving factor on which cell and how many cells we need to use. The next, if you need higher than 3 amp hours or 35 amps current capability, then we need to start looking at the 21700 cells. This is the new class of cells that started several years ago, made famous by Tesla. These cells are used in the Tesla Model 3. With these cells, we can get close to 50 amp output from one cell and around 4 amp hours of capacity. The biggest recommendations we give to customers is to design the BBU to be able to handle both the 21700 and 18650 cell geometry. This gives us the ability to switch between them and makes it future-proof. This shows the roadmap of where the LFP or iron phosphate cells are. The best high rate is about 50 amps current capability and about 2.5 amp hour capacity. In the cylindrical form factor, there are two form factors, 18650 and then 26650. If you go higher than 2 amp hour capacity, you're looking at a 26650 form factor for these cells. So safety is a big aspect of the BBU design. It starts with cell selection and ensuring we pick a cell that is from a reputable vendor and has a long history. We also trust but verify the performance of the cell by running testing at elevated temperatures for years. Some of our BBU cells have been on test for more than 5 years at different temperatures to understand the performance over that span of time. Another thing we do to ensure more safety within the BBU is we reduce the charge voltage on non-lithium iron phosphate cells. Lowering the charge voltage extends the life of the cell and also increases the safety factor. And then to ensure proper thermal propagation design mitigation, we apply gaps between cells and use thermal barriers to prevent heat from one cell affecting the neighboring cell. If you go to the next slide. Every BBU will have a BMS, it's a battery management system. This system will provide the following features. It will monitor voltage, current, and temperature of the cells to ensure they're within normal limits. And if they exceed those limits, it will shut down the battery. It will also ensure our cells are properly balanced. If they go out of balance, it will slowly start cell balancing and try to ensure all the cell strings have the same voltage. The BMS will also provide state of charge readings, so the end application knows how much capacity is left on the battery. This is typically communicated over a communication bus, such as I2C, SM bus, or CAN bus. And then typically there will also be redundant protection features on the BMS, such as secondary overvoltage protection and current fuses. There are also a lot of mechanical design elements that go into a BBU. We need to ensure proper cell spacing between cells to prevent thermal propagation and heat transfer. We also employ wire bonding to ensure each cell is fused on both ends. In case a cell fails, we can quickly disconnect that cell from the rest of the pack. We also look at mechanical enclosure material to prevent any fire leak. Typically, we'll use some sort of sheet metal, but plastic is also an option as long as it is a V0 rating. The goal is to ensure that the project doesn't fail, but if it does fail, then it fails safe. There are a lot of regulations around the world that are tied to batteries. And in the past, it was typically UL 2054 and IEC 62133. But now as new applications are coming forward that are employing lithium batteries, many new standards are starting to pop up that are specific to those applications. And one common test that is new from previous standards is this thermal runaway test. The test procedure calls out that one of the lithium ion cells to artificially be put in a thermal runaway. The test tries to ensure that the complete pack doesn't go into a thermal runaway and fire doesn't escape the case. Again, this is to ensure if a lithium ion cell fails, it feels safe and it doesn't take out the whole battery.
Thank you, Alias. Appreciate your time going through the different technologies involved in the BBU design and manufacture. So I'm going to go through a couple of items that we've been working on within the Open Compute community. And the first one being the Open Edge proposal. The BBU solution we're showing here is for the 3U high, 19-inch wide edge computing product that was started by the Nokia organization. And we're looking at a battery pack that will support a 5 to 8 minute runtime for far edge applications where the power source is unreliable. It's a 1.6 kilowatt battery pack, which is putting out 12 volts of regulated current at 133 amps. And it's a fairly wide temperature range of operation from -5 to 60 C discharge. We do have in the future plans to have something that's going to be able to support an even wider temperature range. This is a full feature battery backup unit with a BMS that incorporates the protection as Alias had gone through, fuel gauging, onboard charging. It's using SM bus communication, and it's designed for a 5-year plus life at about 600 plus cycles. And that's kind of important when you're putting it in an installation that has inconsistent power. We're also, because of that, using a fanless design to increase the MTBF of this product. And we do expect to have prototypes roughly late this year with the base current environment, maybe early in 2021. And we do plan on submitting this to the OCP community. On a slightly larger level, we have the OpenRack version 3 proposal, which is going through development right now. And it's an 18 kilowatt total system power solution and a 2U high, 21-inch wide chassis. And this particular solution is broken down into 6 modules, and it also incorporates a shelf management controller very similar to that of the power supply unit. That's part of the OpenRack version 3 power design. Each one of these modules is at 48 volt and will support a 60 amp discharge. The actual regulation, however, is on a different module that the battery backup unit will plug into that supports the charging and the discharging at that 48 volt plus or minus 1% output. It's a 2U high, it's an open U height, and roughly 520 millimeters deep, and it supports 5 minutes of runtime. And not only is this BBU module parallel stackable within the 2U high chassis, as you see here, but also within the actual system itself. So depending on the amount of runtime that you need for that overall chassis, you can run multiple 2U high solutions. Similar to the OpenEdge product, we're looking at tail end of this year, early 2021. We'll be planning on submitting this to the OCP community. So this wraps up the technical part of our presentation. And what I'd like to do is at least ask the community to please let us know about some of your different ideas of how these BBUs can be used. Always good to hear about specific end applications to ensure that our designs can support it. And let's also make sure that you add information about the thermal management. As you can now understand, it's very critical to the system efficiency and specifically the battery. And we are participating in the telco and edge sub-project as well as the rack and power. So I'm going to open the session up to questions now. Thank you.
Well, thank you everybody for listening into our presentation. It looks like we have one question so far in regards to the NFPA IFC 855 code. So Alias, would you like to take that question, please?
Sure. I would need to look into more details on that requirement and see if there's any concerns with that code for our BBUs.
I do believe that that may tie in with the, I think it's the 9540A and having to do with the distancing between chassis and systems. And if that is the case, I believe that it goes into the design of the pack with gaps in between the cells and doing the testing, such as against the UL 1973 certifications. And a lot of the design will be based on achieving that particular requirement.
And then we also have another question regarding our ORV3 concept and if it's a fanless design. Currently, we do have a provision for a fan in the BBU module. As we run more testing and understand the thermal performance of the pack, we can determine if we actually will need the fan or not. but currently there is a provision for a fan in there.
Sure, and to add to that, there is a revision in the concept since Alias and I recorded this presentation, where it looks more like an integrated design with the charge and discharge module, so it may be all in one unit. And we are definitely doing the thermal analysis. It seems that the charge-discharge portion of it definitely needs more cooling. So we are working with our collaborative partner, Artisan, on that to potentially have 2 fans in the design to be able to support the wide temperature range needed in this application. Okay. Alias, we also have a question about the charge and discharge circuit. And actually our teammate, Navid, who has been working on it, would probably be best to answer that. So we don't know if we can get him tied in right away, but the charging power will not be 3. So go ahead on that, Alias.
Yeah, so the question is the charge and discharge circuit the same power as 3 kilowatts? No, so the discharge is going to be 3 kilowatts. The charge will be considerably less than that. We're still determining what the charge current will be. But yeah, it will not be as same as the 3 kilowatt discharge power. And I don't know if I don't think there's any more questions.
Well, there's a yet. Hang on.
Oh, we do have another question on the chat. It said, can you describe where the charge and discharge converter goes? So as Howie was talking about for our ORV3 proposal, when we recorded this, we were thinking of a separate module that would get attached to the end of the BBU that would do the DC to DC converter. But we're after that there's discussions about maybe we need to incorporate that within the BBU itself. So that's still open for discussion on where that actually will reside.
Yeah, one of the challenges in this particular system is it's pretty power dense. So the cells themselves take up a fixed amount of space, and then we have essentially, I believe it's around 973 millimeters between the faceplate and the bus bar. So what we're trying to do is work with Artisan in this case on coming up with a very compact, power dense, and efficient charge-discharge circuit that's going to fit in there. So when we balance out the space for the interconnect and the cabling and the fans, it's definitely a packaging challenge, and also working within the safety standards of those new certifications, which are going to force us to have a larger gap between the cells than maybe in packs of 5 or 10 years ago.
We also had a question. It would be good to have a selectable charge current 1 through 5 amps. Yes, I mean that will we will be on a communication bus, so we can set the charge current, and that there will be provision to have it selectable within the BBU.
And Alias, we also have a question about a fan in the BBU tied into the NFPA requirements. Do you have any insight into that?
No, I would have to. I mean, we're going to be looking into all that with our regulatory experts. to see, if there's any concerns with putting a fan based on the NFPA requirements in our BBU.
Okay. Well, we will definitely get back with you on that one. The question about cells in series, actually another thing that seems to be shifting, as there are a number of different charge and discharge topologies that were being considered. At first, we were looking at this as a 48-volt nominal, and it would be a buck boost converter, but it seems that we are leaning now more towards a nominal 42 volt, so it'll be a boost only. So at the moment, we're looking at a 12S6P configuration of the cells.
Yeah, and that's being done to help with the efficiencies of the converter.
Correct.
We have another question that says, what is a procedure for locate and monitor potentially problematic cells in the DBU? So we do have we're going to have a BMS circuitry in the DBU that will monitor the cell strings, that will also monitor the temperatures of the cells. So if any of those, if the voltage is too high, or it's in balance with the other cell strings, or if the temperature is too high, it will shut off the DBU as a fail-safe mechanism.
There's a question about 12 volt versus 48 volt, and which is more prominently used in the industry and why. Great question. What we have traditionally seen in the data market is the 12 volt as the more standard bus or backplane voltage. But in the telecom segment, it's been 48 volt for a very long time, minus 48 volt actually. And in our case, what we find is either one of them becomes relevant. We have a lot of customers that are using our onboard modules that are at 12 volts, and what we're seeing is more of the updated UPS solutions in single phase at 48 volts. For us, it does add a little bit more cost and complexity for the 48 volt, just because of the number of cells in series and the balancing and the work that the BMS has to do. 12 volts a little bit easier. But on the other hand, the power circuitry components are obviously with 48 volts a little bit easier and lower cost. So we find it kind of balances out and allows us to have a more reasonable discharge current out of the packs with the 48 volts. So
yeah, I mean, as the power requirements are going up and up for servers, it's easier to deal with that at 48 volts, because then you can reduce the current, and then the I2R losses can be managed, as opposed if you had to do it at the 12 volt voltage.
And a question about locate pack level only. Actually, I'm not exactly sure. Maybe you can clarify on that. Oh, maybe it's in regards, Alias, to the earlier question about the procedure for locating and monitoring problematic cells in the BBU.
Oh, about locate wrong cell. Yeah, I mean, we're not monitoring every single cell in the pack, because that will overcomplicate the BMS. We're monitoring each individual string. So if we go with a 12S or a 14S, each of those strings will be monitored for voltage. And if we detect that the voltage is too high or too low or out of balance with the rest of the other strings, it will shut off the pack as a safety precaution. And then, you know, a lot of our designs were moving to having fuses on each of the cells. So if there is an issue with the cell, the fuse can blow and isolate itself from the rest of the BBU as well.
All right. Well, it seems that we are down to one last question here as we wrap up the half-hour session about the BBU ORV3 boost discharger and buck charger, correct? So Alias, we're taking the 50 volts off of the bus for this, and then bringing it in to charge the packs. Maybe you can just talk very quickly about that.
Yeah, so I mean, like how he says, you know, we're still, you know, we're looking at either a 14S or a 12S, but if it's a 12S solution, we're going to boost up the voltage, and then from a charging standpoint, yeah, we will buck the charger to charge our battery pack.
Yeah, and the charging piece of it is usually going to be designed a little bit closer to the demand of the system as to if there's a multiple discharge requirement, and also how fast that they need the battery to be able to recharge for another full event. Okay, and well, we're going a little bit into overtime, but Alias, do you want to answer this last question?
Yep. Yeah, so the question I'll read it is, are you aware of any design guidelines that allows planning of energy loss and DC resistance increase over past lifetime? This would be helpful in planning a design to meet the system's needs. So if you're talking about the cell impedance, we do model the cell impedance growth over time and over temperature. So, you know, as we discussed earlier in the presentation, we do have cells that are on test over a long period of time at different temperatures. And so one of the things that we get from the test is how the impedance is growing within the cell. So we do model that as we determine lifetime availability of capacity for those for the BBU. So we can determine what the end of 5-year discharge capacity will be, because we will have modeled, you know, the impedance growth of that cell.
Yeah, so in this case, for example, and with most of our UPS and BBU designs, when we give a rated amount of time, it's at end of life. So in this case, we typically design to 5 years. In this case, from what I understand now, it's for a year. So what will happen is that you'll get that 5 minutes at the end of life, but at the beginning of life, you're probably going to be looking at potentially 40 or 50% more runtime available at installation. So it's absolutely built into the configuration of cells and how many we need. And, you know, we do the independent modeling and testing of all the cells that we use in BBUs so that we can actually verify what we're going to be able to put out there as an expectation.
I think, Howie, that's all the questions that we have, and I think we are over our allotted time.
Yes. So thank you, everybody, for attending. And any questions, Alias and I will be available throughout the rest of the afternoon at our booth.
Thank you.
Thank you, everybody.